Good morning, ladies and gentlemen. Welcome back to another video of AP Chemistry with Mr. Kenton. Hope that you guys are doing well today. I know that we've already covered Introduction to Rate Law, but this should just be a good review, a good overview of what we talked about in class last week. And so hopefully you'll find this video helpful. Hopefully it'll help you remember things in case you're forgetting some things. But let's go ahead and dive into this. And hopefully I can do this in under 20 minutes. All right. So remember, as we started talking about kinetics, we made some statements. And one of the statements we made was that we understood that, that rates of reaction are going to increase as concentrations of our reactants increase. Okay. And the reason for that increase in reaction rate had to do with the fact that there are going to be more collisions occurring between your reactants. Right? So there are going to be more opportunities for your reactants to collide, for their bonds to be broken, and then for new bonds to be formed so that products can be made. All right? So that was a general statement that we had stated kind of at the beginning of this unit, and that's something that still holds true here, right? So this concentration piece is very important. Now, the thing is, we've been looking at concentrations, but we haven't been looking at it from a perspective of what is it doing overall. We've been looking at it at given instances in time, specific points in time during experimental data, things like that. And so we want to be able to take the overall concentration dependence, right, of a reaction rate and be able to put it in such a way that it's going to allow us to explain situations for that reaction at any concentration. And so that can be done using the rate law or the rate expression. Now, here's what a general rate law for reaction will look like. So the rate is going to equal to K times the concentration of A to the nth power times the concentration of B to the nth power. Okay? Now, as we saw that A and B, those represents the concentrations of the reactants in your process. The exponents M and N are called reaction orders, right? So reaction orders tell us something. When we change the concentration of this reactant, it has this effect on the rate. The proportionality constant K, that's our rate constant, right? Remember, this rate constant is going to be unique to each reaction. And the other thing we can look at is that we can determine the overall reaction order by taking a sum of the reaction order. So simply taking the sum of the exponents of our reactants in our rate law. And so for this general sense, our overall order of reaction would be M plus N plus ... depending on how many reactants you have in your rate expression. Now let's take a look at an example. So we've got the reaction that D plus 2C yields AB. Now, in order to determine rate laws, it's important for us to recognize that it has to be determined experimentally. Okay, so experimental data is what is used to determine the rate law or the rate expression. And so we carry out the reaction, several different scenarios, and we determine that the rate law for this reaction is rate equals K times the concentration of D to the 0th power times the concentration of C to the 1st power. So this portion right here, this is our rate law for this reaction. Now, the reaction is 0th order with respect to D and 1st order with respect to C. And we can see that from the exponents that we see with D and C respectively. Now, you might be wondering, what does that mean? And so for something to be 0th order like D, that means that when we change the concentration of D, that it does not change the reaction rate. Okay, so changing the concentration of D has no effect on the reaction rate for this particular process. All right, now what does it mean for C to be 1st order? Well, if we change the concentration of C, the reaction rate is going to change by that same factor as well. So for example, if we double C, that means that we would anticipate that the reaction rate will also double. And applying that last little bit from the previous slide, if we wanted to know the overall reaction order for this process, we would say that it's first order, right? Because take 0 plus 1, that gives us 1. Makes sense so far. Pretty straightforward, I hope. All right, so let's take a look at a more specific example of something that actually has actual chemical species. So let's say we consider the reaction of ammonium ion plus the nitrite anion, and it produces nitrogen gas and liquid water. So you carry out this experiment, you do it several times, and in each of your experiments, you're testing things and you're trying to figure out what's the relationship between the rate of the reaction and the concentrations of ammonium ion and nitrite anion, okay? And so you carry out your experiment multiple times, and here are the observations that you make. You notice that when you double the concentration of ammonium ion, that the rate will double as long as the concentration of NO2 minus is held constant. Now, the reason why we held NO2 minus constant is so that we could make the distinction that changing the concentration of NH4 plus is the reason for the rate doubling, right? This is that idea of isolating your variables so that you have your independent and dependent variables kind of isolated so you can make conclusions, right? Likewise, you note that when you double the concentration of nitrite, the rate also doubles when the concentration of NH4 plus, the ammonium ion, is also held constant. So for both of those ions, we're seeing that they have the same impact on the rate when we change their concentration, right? So based on those observations, the rate of this reaction would be expressed in the following manner. We would say that the rate of this reaction is equal to K, the rate constant, times the concentration of NH4 plus to the first power, times the concentration of NO2 minus to the first power. So we're saying that NH4 plus and NO2 minus are both first order reactants, right? And so some things that we can mention here, we could say that the reaction is said to be first order with respect to ammonium, and it's first order with respect to nitrite. Now again, our overall reaction order for this process would be second order because 1 plus 1 is 2. All right. And I know I've mentioned it, but please keep in mind that reaction rates come from experimental data, not stoichiometry. Notice that we said we carried out the experiment and made these observations. We didn't use the stoichiometry of this process to help us come to the conclusion that NH4 plus was first order and NO2 minus was first order. We're going to constantly be coming back to that particular point here, right? Reaction rates come from experimental data, not the stoichiometry. Okay. All right, so now let's talk about these order of reactions. I've mentioned zeroth first, second order. What exactly does that mean? What is that telling us? And so if a reaction or a reactant is zeroth order, that means that when you change the concentration of that substance, it produces no effect, it produces no change in the rate of reaction. Okay, so zeroth order, changing the concentration, has no effect on the reaction rate. Now, we've seen first order a couple of times now, and we even saw 2 slides ago that we talked about that when we change something, the rate's going to change by that same factor if it's first order. So reaction is first order or reactant is first order in the situation where if we change the concentration, it causes the rate to change by that same factor. Now here I've given you a specific instance, right? If I double the concentration, the rate's going to double. Now, a reaction or a reactant is second order if you make a change in the concentration, then it's going to cause an increase in the rate that's equal to that change squared, right? So for example, if I double the concentration for something that's second order, what I would anticipate is seeing that the rate would increase by a factor of 4. It would quadruple. All right, if it's third order, what I'm communicating is, all right, if I change the concentration by some factor, it's going to lead to increasing the rate by that factor to the third power. Okay, so if we use our specific example, if we double the concentration, it's going to lead to an increase in the reaction rate by a factor of 8 if that reactant is third order. And so those are those definitions. That's the breakdown of the order of reactions. Can there be other orders of reaction? Absolutely, but 0, 1st, and 2nd are going to be the most common things that we're working with in our context. Now, obviously we've been looking at rate law, rate expression. The rate constant K does not depend on concentration, right? There are other factors that might influence K, but the concentration is not going to have an impact on K. Regardless of your concentrations, the rate constant K is going to be K, right? It's going to be that factor for that reaction. Now, the nice thing is once we've determined the rate law and we've determined the rate constant, this gets back to kind of our original purpose of wanting to look at this, we can then use those expressions and that constant to calculate initial reaction rates under any set of concentrations, which is really helpful, okay? Because the reality is you might be given a process and you might be starting off with very different concentrations, and you would want to know what's the initial reaction rate. And if you have that rate law and rate constant, you'll be able to do that no problem. Did I mention that the rate law is determined by the experimental data and not the stoichiometry? I think I have, but just to remind you, right? Coefficients in the reaction have nothing to do with the rate law. The rate law can only be discovered experimentally. All right, let's talk about this rate constant a little bit more, right? The rate constant K is dependent on each reaction and the conditions for that reaction. Let me just pause there for a second. That means every reaction has its own unique K value. It's kind of weird, but it's still going to be a constant for that reaction, but it's not like a universal constant like we would say like the speed of light, right? Now, temperature is a factor that's going to influence K's value, but for now, we're not going to take a look at that until much later on in the unit. Now, the units for K, you might be wondering, okay, well, it's a constant. What are the units for this constant? Well, the reality is, that's going to depend on the reaction order. Now, as a rule of thumb, the units for K are going to be 1 over m times n to the minus 1 power times time. So 1 over m to the n minus 1 power times time. Now, n is going to be the reaction order, so the overall reaction order. Time is going to be whatever units for time you're dealing with. And so when we're taking a look at the reaction that we looked at, we know that we had a second order reaction, right? So it was K times NH4 plus times NO2 1 minus. So the units for K would be 1 over m times time, because it was second order. 2 minus 1 would give us 1. So 1 m to the first power is simply m. And so 1 over m times time would be our units for the rate constant for the example reaction that we saw before. Okay. Now, last thing we need to do is look at 2 examples. And again, I know that we did these in class, but again, it's just good to kind of take a look at them. So we've been given reaction A plus B yields 2C. And what you should notice is that you've got 5 different experiments that have been carried out. Okay, and so what we're going to be tasked with doing is trying to isolate experiments to where we can find changes specifically in A and changes specifically in B. Now, for me, one of the things I want to do is I want to find an experiment where A and B are very similar, right, if not the same. And so experiment 1 is going to serve as our baseline for making our comparisons for reactant A and reactant B. Now, if I wanted to determine the order of reactant A, what I would need to do is I would need to look at the experiments that have been done, and I need to look for cases where the concentration of B was held constant. Now, looking at the experimental data, what we see is that in experiments 4 and 5, the concentration of B was held constant, right? Now, because of that, we can then use that experimental data to figure out what is the order with respect to A. Okay, now I'm simplifying this a little bit, but what we know, we can see, is that if we look at this, the variables and the components of B are just going to simply be 1. So that factor can almost be ignored in this case. So like if I take experiment 4 and experiment 1 and I compare them, what I'm going to have is we know that this needs to be to some exponent that we don't know. So it's going to be 2 over 1, so that's 2. So 2 to the x power is going to equal to the rate of 4 divided by the rate of 1. So you got 0.060 divided by 0.015, and last time I checked, that was 4, right? So 2 to the x equals 4. Well, to get 2 to the x equals 4, that means that A has to be second order, right? Now that I've identified the order of A, I need to look at my experiments and figure out, okay, are there any experiments that allow me to determine the order of B while holding A constant? And the good news is experiments 2 and 3 can be used to determine the order of B, right? And so again, we'll be able to make those same comparisons, right? We're going to have rate. I just like to use the simplest one, so like experiment 2 and experiment 1. I'd have rate 2 over rate 1. So we've got and all of that information. So the A information, it's all going to be 1 because we already know those particular pieces. Even if we plugged in the 1 squared is still 1. 1 divided by 1 is 1, right? So A is a non-factor. So then we got 2 over 1 for B. So we got 2 to the x power, and it has to equal the comparison of the ratios of those rates. So 0.030 divided by 0.015, that's 2. Well, that means that B is first order. Okay. Now, the good news is, if we wanted to figure out A and B, we could have used experiments 5 for A, and we could have used experiment 3 for B, and we would have gotten the same data, right? And so now that we've identified the orders, we know the rate law for this reaction would be K times A squared times B to the first power. Now that means that the overall reaction order is 3. And so then what we can do is we can use one of those experimental data lines and we can solve for K, right? And so if you're looking at this particular problem, how it's been worked out, they took experiment number 2 and they used the value. So we've got the rate, 0.030 molar per second equals K times 1.0 molar squared times 2.0 molar. And so when you simplify that, you're going to end up with 0.030 molar per second divided by 2.0 molarity cubed. And when you do that, you simplify it. The units here are a little off. It should be 0.015 divided by molarity squared times seconds. Okay. Hopefully that makes sense. And again, if you need to watch that again, feel free to pause the video, go back and look at that. All right, our last example, and then we'll be done with this video. Let's say that we're given a smaller set of data, and in one of our scenarios, we're able to isolate the change for one of our substances, but we're not able to isolate the change for the other substance. And so, like when I look at this again, we always want to find what's going to serve as our baseline. And so, for example, experiment 1, that serves as our baseline. But then when we look at it, let's see here. For A, we have a situation where for A, we can make a distinction, right? So we could figure out for A, so A increased by a factor of 4, so this is 4 to the x equals, our B term is just going to simply be 1, so we can remove that, and the rate increased by a factor of 4. Well, that means that A is first order, right? Now, when we look at the experimental data, when we look at experiment 3, while the concentration of B changed, the problem is that the concentration of A also changed. And so what we're going to have to do is we're going to have to plug in the information that we now know, A is first order, so that we can compare two different reactions to solve for B specifically, right? And so like what you can see here is we used experiment 3 with respect to experiment 1. And so, and I think there was at least when I looked at this, I think it's been kind of confusing of the N's and the L's and things like that. So I'm going to rewrite this because I think some things got plugged in incorrectly. We got the 0.80 divided by 0.20. And if we're doing experiment 3, what we can see is that it should be, so it would be 2.0 molar. Now A, we know, is to the first power, times B, which is going to be 2.0 molar. And in this case, they're saying L power, right? And that's going to be over, for reaction 1, it's going to be 1.0 molar to the first power times 1.0 molar to the L power. Now, if you're following along here, we also have the rate where it was 0.80 divided by 0.20. That's 4. So what we've got set up now is we've got 4 equals 2 times 2 to the L power, right? Now if we divide both sides by 2, we've got 2 to the L equals 2. So that means L equals 1. So that means that B is also first order. Okay. Now, since this reaction is first order with respect to B, that means the rate law is K times the concentration of A times the concentration of B. Now the reaction is overall second order. And so then we can go through and we can solve for the value of K just like we did before. We take one of those experimental lines, plug in those concentrations, maneuver the rate constant so that you end up with your value. And again, the units here for the rate constant, that should be, I believe it's 0.2 divided by molarity times seconds. Okay. And ladies and gentlemen, that's how you would determine a rate law, a rate expression, and solve for the rate constant for a given reaction by using the experimental data that's provided to you. I hope this video was helpful. If you have any questions, please don't hesitate to ask, and I look forward to seeing you guys again soon. Thanks, and take care.